For this problem, we're being asked to find the integral of e to the x using the Riemann right-hand rule. And so working from the equation that's associated with the right-hand rule, and we fill in our interval of 0 to a, then we end up with this expression here in the first line. Now, if we simplify that, because we have a minus 0 over n, it becomes a over n times the sum from I equals 1 to n of e to the I a over n. And so if we have a look at what that looks like when it's expanded, we are looking at the limit as n approaches infinity, and we have a common factor of a over n, so we'll keep that out front. And the first term in our series is going to be e to the a over n, and then the next one will be e to the 2a over n, because now I equals 2, and then I equals 3, so we have 3a over n, and so on. And that's going to keep going all the way up until we actually have n times a over n, which is just going to give us e to the a. So this is a geometric series. For a geometric series, when we want to find the sum, the formula that we're going to use when r is greater than 1 is a times r to the n minus 1 over r minus 1. So we need a and we need r. So a is our first term, so that's e to the a over n. And it actually turns out that r, the common multiplier from one term to the next, is also e to the a over n. So we're going to sub those into the sum of a geometric series formula and see what happens. Okay. So if we sub those into our formula, we end up with e to the a over n times r, which is e to the a over n, and that's to the exponent n minus 1 over r minus 1, and r is e to the a over n again. So we know that the sum and the integral of e to the x is really the limit as n approaches infinity of this expression. Sorry, that's just e to the a now. All right, so we're going to run into a little bit of trouble when we try to evaluate this, because we're going to end up with a denominator of 0, and so we won't end up with a defined value for our limit. So to get around that, what I'm going to suggest that you do is make a bit of a substitution here. And this is as far as I'm going to take you. I don't want to do the whole problem for you here, but I'm going to take you to the next step and show you a substitution that will make things a little bit easier. If you are to substitute a over n, let's let it equal another variable h, then we will end up with e to the h times e to the a minus 1 over e to the h minus 1. And because we have e to the h, now what we want to do is change this expression, and the equivalent expression is going to be the limit as h is approaching 0, because we don't have the denominator anymore, of e to the h times e to the a minus 1 over e to the h minus 1. Now that we have the limit as h is approaching 0, we are allowed to use L'Hopital's rule to differentiate the top and the bottom separately. And so if you do that, you will find that your antiderivative, your integral that we're looking for, is going to come out to x to the, sorry, not x, e to the a minus 1, which makes sense because remember what we were integrating was e to the x over the interval 0 to a. And so we know that e to the x, using the derivative rules, the antiderivative of e to the x is just e to the x. And so substituting in our top interval value, we would get e to the a minus, and if we substitute in the bottom value, we would get e to the 0. So we would have e to the a minus 1. And so I'm going to leave it up to you to use L'Hopital's rule to differentiate the top and the bottom of this expression and have it come out to e to the a minus 1. And that's the first part of this assignment. So I hope that's helpful.